Bottke on what really happened to Earth's older craters.
Okay. A couple things before we get going here. This project is the thesis work of Sarah Basrael, who is I don't know how to use the pointer here. Oh, there we go. Okay. She is the grad student of Becky Genn at the University of Toronto, and this has been a really fun project. We keep adding people as we find out new things. One of the things is I have a 6 o'clock flight tonight at San Francisco, so if I'm not here for the question period, it's either because I'm running for the flight or it's because I want to dodge all interesting questions, right? So we'll see which one works out that way. Okay, so ever since I was a grad student, I've been trying to understand terrestrial craters, and there's really interesting mysteries involved with them, and I haven't been able to make any sense of things. So here's a plot showing all of the terrestrial craters we have on the Earth. You can see that they're kind of patchy. There are places where we have lots of terrestrial craters. There's other places where we don't have many. And all told, there's a little bit less than 200 craters all across the Earth. Now, if we take the larger ones, those are like, let's say 20 kilometers in size or even 5 kilometers in size, and you plot them up, you get kind of an interesting distribution. You'll see that there's lots of younger craters. Can I do this over here? Nope, I'll do it over here. Okay, I'm going to use my finger. Okay, good. So, what's that? I'm going to give up. You'll just have to get the idea. Okay, so essentially that there's a lot more younger craters and there's very few older craters. And typically this is attributed to erosion. This is what we learn. This is almost a mantra we learn in our classes. But I've always wondered, how do you know if that's true? How do you really have a feeling for that? There's also the fact that when you get beyond about 650 million years or so, there are almost no terrestrial craters on the Earth whatsoever. And why is there such a deficit beyond that point? So I wanted to see if we have some way we could test this. But most of my career we haven't had a chance to do that. In this talk, I'm going to try to show you some new results where I think we can really get at this, and it led into a really interesting place. Okay, so one way to get at this problem is to go to the moon, right? Because the moon didn't suffer the wind and water and all the other erosion that the Earth has. So if we can understand the moon's crater record, we can make a direct comparison to the Earth and say some things. So one way to get ages of craters on the moon is to go to a given crater, and then you count superposed smaller craters on its surface. So here's some counts by Michelle Kirchhoff and the rest. And that gives you a relative age. And if you have some idea of the production rate of those small craters, then you can get an absolute age, and it works really well. The only thing with this is it's a really painstaking process. People like Michelle and also Stuart Robbins over here, they put all this work in to get these things. And also, I would say, when you go to smaller craters, let's say smaller than 50 kilometers, the surfaces available to you to get a good crater age for that is very difficult because they're small. And so then you have to go to higher resolution images. And in the end, it's just, the question is there an easier way to do this? And I think the answer, interesting enough, may be yes. Okay, so this talk takes advantage of some really interesting work that's coming out of LRO's Lunar Radiometer. So what this instrument is it measures the moon in 3 different infrared channels, and essentially it measures temperatures on the moon. Okay, so you get temperatures all across the moon. And the way to think about it is this. So the question is, like, what temperatures should we expect? Okay, so if you go to the beach on a really sunny day, the beach is really hot on your feet, and you don't want to stand there. But then as soon as the sun goes down, the sand cools down really quickly. Okay. On the other hand, rocks take a long time to heat up, but once they're hot and the sun goes down, they're still hot for a long time. And that's because of the different thermal conductivities of sand versus rock. So the same thing is true on the moon. The regolith has certain properties, the rocks have certain properties. And so if you take a look at the moon from what Diviner says, you go from an image like this to more like an image like this. And what happens is that all the rocks, all the blocky areas just jump out at you. And when Becky was visiting our department at Southwest a few years ago, she showed me some of these images, and I started to get super excited because all of the young craters just jump out at you because they happen to be all rocky and blocky. And I thought, wow, this is really cool. And so Becky actually took these kinds of results and did something which I thought was really interesting. So what she wanted to do, first of all, is sort of get a relative age for different craters. So imagine you have a fresh crater that's just formed. Okay, imagine like Giordano Bruno. So that's a very, very rocky crater. But then over time, small little impacts and thermal cycling for the moon will gradually break down your rocks and boulders and change them into something more akin to regolith. And eventually, at some point, you sort of fade into the background. And And we think that after about 1 billion years or so, almost everything looks like the background. You can't say very much. But over the last 1 billion years, we can say some things about craters. So we can use this to get relative ages for craters all across the moon, provided they're less than 1 billion years. So then the question was, could we actually get absolute ages? And Becky's work in 2004, I think, really pioneered an interesting way to do this. So what she did is she got the rock abundance ages, or essentially a statistical measure of rock abundance for all sorts of craters where we think we have reasonable absolute ages, craters like Tycho, craters like Copernicus, and others. And then she plotted the crater age versus this measure of rock abundance, and you can see it's a fairly much, it's a linear progression, right? So we can use this relationship to now date craters all across the moon. And that's what you see in the plot. This is just color-coded. But so what we've done is we've taken the colors represent different ages, but we've measured, or I should be careful. Becky and Sarah have measured craters, rock abundances all across the moon. They've used this relationship to get ages for these craters. Okay, so this is actually quite exciting. It's a real advance in the way to think about things. Okay, so if you take all the results that they've obtained and you plot them up, in this plot we can go back about 1 billion years, but here I'm only showing about 650 million years. Once you can plot up all the ages we get for 10-kilometer craters, and what you notice right away is it's not exactly a straight line, okay? It actually has some features in it. And actually it seems like there's a break in it at some point. So we brought in Alex Parker to do this project because Alex is sort of I would consider him the master of statistics. He certainly knows more than I do, right? So we asked Alex, okay, take this relationship and tell us what you see using all your special tools. And what he found is it seems like there's a break in the impact flux on the moon that happens roughly about 250, 290 million years ago or so. And the impact flux actually increases over recent history, and we think the increase is about a factor of about 2.6 from this work, okay, give or take the error bars I show there. So that's a pretty sizable influence, or increase. And so you could ask, well, why does this happen? I would say the most likely way it happens is that we have asteroids that break up in the asteroid belt, they produce fragments, these fragments escape the asteroid belt, and eventually they can actually increase the overall flux on the moon for hundreds of millions of years. We've seen this in lots of different modeling work. I could say more about that, but I'm supposed to talk about terrestrial craters, so we're going to come back to that. Okay, so here's the moon for 10-kilometer craters. We can also do the same thing for 20-kilometer craters, and you see we get about the same relationship. And so at some point we're writing the paper, and I thought, well, we should probably make a comparison to the Earth. But I almost didn't do it because I thought, well, the Earth is so biased, it's going to be useless, right? So then I, just for the sake of doing it, I plotted it up, and all of a sudden I found that the Earth craters and the lunar craters are surprisingly similar. In fact, Alex would say statistically you can't tell the difference between those two different curves. And so this would suggest that the Earth is also seeing a much higher flux of impacts over recent times. And as you go back further in time, you have fewer impacts, but it's not because of erosion, it's because the impact flux was actually lower at those times. So that's really interesting. Okay, so that's a provocative thing to put into a paper, though. So then we had to prove it. Okay, so we had some interactions with the referees, and they said, all right, you got to prove this to us. So here's some ways that we're going to try to prove it. I'm going to try to make a case to you as to how we proved it. So the first way, which I thought was the simplest, is just to look at the size distributions of the craters we derived on the moon and the craters on Earth, and we wanted to see if there's any differences. And from a statistical standpoint, those two curves are basically the same, even at small sizes. We don't see Earth craters sort of fading off to nothing. It's basically the same shape we see on the moon. So that's one piece of evidence that erosion is not a big deal. Okay? But the referees were still like, no, that's not enough for us. Okay, so this is where it's nice to have chance encounters. So I went to the Goldschmidt meeting last year, and I sort of had all these ideas in the back of my head. And through meeting a guy, and we were drinking beer, he introduced me to a whole bunch of other guys, and I think they helped us crack this problem. So I met a guy named Tom Gernon, who's this really good young geologist from the UK, and he did his thesis work on kimberlite pipes. Okay, so if you don't know what a kimberlite pipe is, it's a volcanic construct. So you have a deep sort of mantle-sourced volcanic product that's coming close to the surface. When it gets within about 1.5 to 2 kilometers, it explodes upward, and it makes almost like a little carrot-like structure. And these structures are very similar all across the Earth, and they can tell you a lot about the nature of that volcanic event. But what they also can do is they can tell you a lot about how much erosion has happened in a given place on the Earth. And what's interesting is that most of the kimberlites we find on the Earth are actually on the most stable regions we have on the Earth, the cratonic regions. Okay? So we can plot up all the kimberlite pipes we have, and then we can compare that to where we have the craters. And the craters and the kimberlites, for the most part, lie in the same regions. Okay? Not surprisingly, because those are the most stable regions we have, and you kind of expect craters to survive on these stable regions. In fact, about 85% of all of our 20-kilometer craters are found on these cratons, right? So if we take all this, and so Tom is an expert, so he went into the literature, and he plotted up essentially all of the crater ages we had on different continents, but then he also plotted all of the kimberlite pipes that we had, and he looked in the literature to see how eroded they were. So all these different colors represent different parts of the kimberlite pipe, the diatreme, the hypocil, and so forth. And what he found is, for the most part, the kimberlite pipes are just not that eroded. At the best, they're eroded at the few 100-meter level, okay? And that suggests that the craters simply aren't that eroded either over these times. And also, these results of this very low erosion rates agree with recent results from Blackburn et al., where they used lithospheric thermal histories to look at the cratonic erosion rates, and they also got erosion rates on the order of a few 100 meters. So there's just not that much erosion here. So that actually fits with our story very well. Okay, so now we have this nice plot, but we still have this issue. Okay, so now we have maybe an understanding of what happened in early times. But you'll notice that about beyond 650 million years, there's no craters. But if there's low erosion, we should have a bunch of craters there. So what's going on? And then we have these two craters sitting out there 2 billion years, Sudbury and Fredefort, which are huge. Okay, so how do we explain this? This seems like an issue. Well, then again, these other guys I met at Goldschmidt actually were experts on this other elements of it. And so we want to understand why there's few craters here. And so I told them my story. I had some hints of what was going on, but immediately they got excited because what they do is actually work on something called Snowball Earth. Okay. So the issue is that we think somewhere between about 650 and 850 million years ago or so. And there was probably multiple episodes of this. Glaciation went from the poles, and glaciation actually reached all the way to the equator. It may have actually encased the Earth in ice, although there's debate about how much ice was on the oceans of the rest. But when these glaciers advanced, they actually carved up a lot of the continents, and they probably removed multiple kilometers of material. Okay? So eventually, the Earth got out of these Snowball Earth events by high CO2 in the atmosphere. And so you melted all the glaciers, but most of that erosional material ends up down into the seafloor and gets subducted. Okay? And the people I was working with, that's what they do. They worry about the subduction of this material and what happens from this. In fact, what they point out is that this evidence for lots of erosion exists in a lot of different places, including if you've ever gone to the Grand Canyon. They have a thing there called the Great Unconformity. There's a huge amount of material that's missing. They argue Snowball Earth erosion probably caused the Great Unconformity. Almost done. Okay, so if you put this together, we have lots of erosion that's getting rid of all the craters, and that's possibly why we don't have any at beyond 650 million years. But then these two craters that are standing out there, if you look at them from a geological standpoint, they look like they've experienced multiple kilometers of erosion, but not enough to erase the craters. So this whole story seems to fit together pretty well. So what this suggests is that we have a good story for the younger craters on the Earth. We have a change in the impact flux. We have Snowball Earth episodes that have removed older craters, but some still survived because they were big enough. Okay, so that's the story. And so I'll put up the conclusions, and I'll just take questions. So thank you.
We've got time for a couple questions.
I knew Kevin was going to ask something.
Well, no, you should get a question. Let's see, Gene Shoemaker used to say this back like 30 years ago. The same thing about the hit from terrestrial craters. He always said that the recent impact rate was a lot higher by a factor of 3 than the previous. So you're following in the great man's footsteps, and that's a good thing.
If I could ever be mentioned in the same name as Gene Shoemaker, that's a good day, all right? So, no, Gene had incredible insights, and yeah, he did advocate for this more recent increase in the flux. And I think, I've been suspicious of this for at least a decade or more, but I think this work that Becky Gent and Sarah Masriel have done really, I think, nails it. And they've done it in a quantitative way as opposed to what Gene did, where he's playing around with terrestrial craters. Well, he's got 4 craters. He's trying to do statistics on 4 or 5 craters. It's hard. But now I think we have a story that makes sense. So I'm happy.
All right.
Okay, thanks a lot.